Controlling the polymorph formation is a necessary step in our drug discovery and development. An in-depth understanding of the polymorphic transformations, their thermodynamic relationships, and control of such transformations is imperative. In a polymorph screen, we are trying to discover how many polymorphs the API has. When we observe multiple crystal forms, we must put them through a variety of tests to identify the interconversion and thermodynamics between the relevant forms, such as anhydrates and hydrates. Let's take anhydrate forms for example. There may be cases where one form is monotropically related to the others, meaning that it is thermodynamically more stable across all temperatures. On the other hand, there may be an anisotropic relationship between forms, indicating that in one temperature range, one form is more stable. But after crossing the transition temperature, a different form is now more thermodynamically stable. In general, the most thermodynamically stable form will have lower solubility, while a metastable form will have higher solubility. Some metastable forms, once isolated, can be very stable for longer periods of times, and these can be considered a good candidate depending on the underlying properties, such as solubility, particle size, morphology, bioavailability, and the risk of conversion to another form under long-term stability. The Gibbs free energy gives a convenient means for examining the underlying stabilities of different polymorphic phases. However, there is no direct way to measure the Gibbs free energy. And this is where we can use the Gibbs-Helmholtz equation to derive and get the temperature dependence of equilibrium constant. Gibbs free energy diagrams can utilize solubilities at various temperatures to graphically represent the thermodynamic stabilities of different crystal forms by plotting the natural logarithm of the equilibrium constant against the reciprocal of the temperature. This is what is known as a Van 't Hoff plot. To establish the monotropic or anisotropic relationship between different polymorphs, thermodynamic solubilities of the polymorphs can be obtained at various temperatures. And these resulting solubility and temperature data can then be used to generate the Van 't Hoff plot. It is crucial that the forms used in the solubility experiments do not change forms, or the values will not be representative. In our case, we utilize XRPD at the final time point to confirm that no polymorph conversion occurred. For anisotropic systems, the Gibbs free energy diagram would show trend lines that intersect at a specific temperature, where the solubilities are equal. In this case, above the transition temperature, one form would be more stable, and below the transition temperature, the other form would be more stable. For monotropic systems, the trend lines do not intersect, and the forms with the lower Gibbs free energy is considered the most stable over the examined temperature range. Determining the thermodynamic relationship between polymorphs can be complex, and many techniques such as competitive slurries, DSC experiments can be utilized to probe the relationship. A combined approach is always recommended to ensure that the results are consistent across experiments. And a Van 't Hoff plot is a reliable method for confirming that the most stable form is selected for further development.